My name is Sergey Sverchkov. I'm from Altoros company, and on current session we will be discussing approaches how to evaluate different NoSQL solutions, data stores in terms of performance and features which they can provide. I apologize in advance if I have some pronunciation or grammar errors in my speech, because I'm non-native speaker. So feel free to stop me and ask questions if you cannot understand clearly. So NoSQL solutions feature elasticity and scalability, and they became very popular in the last 2 years. Why did NoSQL solutions appear? It's mostly because relational databases have a number of restrictions when you have to deal with big amount of data. First of all, they are hard to scale in terms of write operations. Sometimes it's difficult, expensive, or impossible. Vertical scaling, when you try to migrate to the bigger hardware, is also limited and expensive. And horizontal scaling is available in some platforms. It is available, and but in most cases for write operations you cannot scale horizontally, adding new nodes. Also, there is a problem if you need to change data schema, because in relational world you define a data schema, and when system runs in production and you need to change an objects in a database, you have to define a scenario how to upgrade the system, how to apply new schema to the database. Sometimes it leads to significant downtimes in production systems. Also, there is a problem with a different presentation of objects in an application layer and presentation of data in a database, because in a database the object can be divided in several tables to have a normal model, and to provide data to the application, we need to retrieve data from different tables. So it leads to object relational impedance mismatch. So the biggest, I suppose, the biggest problem among these problems is scaling and performance issues. Some solutions, for example, like Oracle, they provide not a scaling, but you can run a database on several instances, but the database itself, the data files, they reside on a shared storage. In MySQL, we can scale read operations, but write operations, they still go to master database and then replicate it to slaves. So we can scale read operations, but we cannot scale write operations. So why we need to evaluate or choose the right solution. So right now there are almost 150 different solutions. They fall in different types. So we have a k-value storage, we have a columnar databases, we have a document databases, and we have graph databases. NoSQL solutions, they don't use relational models, so most of them do not provide a query language. They are often referred to as schema-free with flexibility in defining a model, or even you don't have a model at all. For example, if it's in a k-value storage and is it used, and k-value storage is used, for example, to cache the data, we just have keys, and we have a value which can be just sequence of bytes. Most of solutions provide a API to access the data, and some NoSQL stores provide a certain notion of query language. For example, in Cassandra we have CQL, Cassandra query language. HBase provides a Hive that can be used to query data and to implement, for example, join operations. But there is no standard, so they operate with eventual consistency instead of strict consistency in relational databases. It means that in a distributed system, at some point of time, all nodes in a cluster can have a consistent state of data, but it takes a time, and it should be noted in system design. And one of the biggest challenge is that the system they're designed to run in a cluster and provides ability to add new nodes and to scale the amount of storage, the amount of memory which is provided by a system. So this type of scaling is often referred to as horizontal scaling. So how we evaluate different solutions? First, we can group different solutions in a data model. It's not a data model. It's rather a type of how the data is stored inside a database. Key value storage, the data inside key value storage, they are uninterpreted sequence of bytes. In a document databases, for a key, we have in most systems we have JSON documents, and JSON documents we can query attribute of a document, and it provides more flexibility in terms of how we operate with the data inside a single document. For columnar databases, we have a set of columns which are associated with a row key, and the graph database is a separate class of NoSQL solutions which are designed to work with heavily linked data. So they provide API. Most of the system they provide a REST API. Some of systems provide query languages, so we can evaluate if if it's optional for a system to have a high-level query language. Some of solutions provide a MapReduce support. For example, in Mongo database, we can compile MapReduce functions in JavaScript. There are different approaches to control concurrency. For example, there is a multi-version concurrency control when for every change of data, new version of row is created. Or there is an optimistic locking mechanism when before updating the data inside the database, it is checked if the data is changed or not. There are different strategies to partition data. The first strategy is based on the range of case, and the routing server splits all the case in the ranges and assign a range of single range of k to the node, to one node. And when we query the data, the routing server provides the pointer where data is located, on which node the data is located. Another strategy is is based on a hash function, which the hash function returns for a specific key value. Returns a range and also identifies where the key and the data for a specific key are located on which node. Also, we have to deal with replication and consistency. Almost all solution provides storing several replicas of data to provide failover in case of physical failure of one or several nodes in a system. It can be a trade-off between availability of system or consistency. So, for example, if we set a strong consistency, which requires the data are written on all nodes before returning the result to the user, we'll have the availability of system will be lower because if one node fails, in that case the system cannot provide the result of operation. And we can evaluate performance. The performance evaluation, for example, we can evaluate building a small version of a system and running a workload which is typical for our application. But there is also an approach when we can use the set of typical workloads and the tools which can generate the workload. For our test and benchmarking, we used Yahoo Cloud Serving Benchmark. It's a framework that contains workload generator, and it defines a set of workload scenarios to run simple operations over the database, or it can be a relational database, it can be NoSQL solutions. So basically, workload is defined which operations to perform and which records should be read or updated. The operations are supported. They are simple: insert, update, a read operation, and there is a scan operation. For most of workloads, the operations they are generated in a random way, so we can run different operations at the same time. To evaluate NoSQL solutions, we used table which contained 100,000 million records. Each record was 1 kilobyte, less than a kilobyte, and record contains 10 fields. The fields are named very easy. Field 1, field 0, field 1, field 10, and every row in a table is identified by a primary key, which is defined like the value user 2, 3, 4, 1. The data in each field are random strings of characters. So every field 100 bytes. To run a workload, it was divided in two phases. The first phase is load phase, when we upload the data in a data store. So the amount of data for all tested solutions was the same, and then we run several sets of transactional workloads. It's a component diagram for YCSB. As a developer, you should define which databases to test. So we define a database connector. We define how many concurrent threads should run and execute the workload over the tested solution. And we define target throughput. Target throughput, it is an amount of operation which we want to apply and which we want to apply to the database. So the workload executor starts the specified number of client threads, and all the operations, they are divided between client threads. For example, if we have 100 operations and we have 10 threads, each thread runs 10 operations. Each client thread reports the statistics of execution of operations to statistics module, and then statistics is printed, for example, either to command line console or to the file. So essentially, we applied the same approach to several NoSQL solutions. The environment for tests. So we used Amazon AWS. All nodes were started in one region in Ireland, in one availability zone. The nodes which actually store data, they were a type of M1 X large. And the storage was created as elastic block storage volumes, 4 elastic block storage volumes. Each volume contained 25 gigabytes, and 4 volumes, they were assembled in RAID 0. So every data node contained the storage of 100 gigabytes. So totally the cluster had 400 gigabytes. Why CSB client? It was deployed and started on a separate node, the type of node C1 XLarge. And for testing Mongo database, we used two additional nodes. They're quite small and type C1 medium. All instances were configured with the same security group, and before running a test, we configured all required ports in the security group, and then started sequentially test for every solution. This slide contains specification for nodes in our testing environment. Just one additional comment. So elastic block storage volumes, they were a type of EBS optimized. We didn't use provisioned IOPS volumes. So we used, let's say, simple EBS volumes. Which databases we tested? In this particular, for this particular presentation. We tested Cassandra 2. It was configured with some non-default settings. We installed it with JVM 1.7.40. It used random partitioner. It's a default value for partitioner. We set the size of cache for keys to 1 gigabyte, the size of cache for rows to 6 gigabyte, and additionally we configured Java virtual machine heap size to 6 gigabyte. For all tested solution, we used a replica factor as 1. So no replicas were created for the data because we just wanted to test the performance, not the fail tolerance of system. The second solution is Mongo database 2.4.6. Just a couple of configuration settings from default installation. 2 additional nodes for Mongo router process. In our previous tests, we discovered that Mongo router process it consumes quite a lot of CPU, and the guys from Mongo, they recommended to run Mongo router process on separate instances. So the sharding was done by internal document key ID. The next database is Couchbase. So not too much settings, just we set the memory and disk mode. So by default, the Couchbase runs all data in memory, and if the data does not fit in a memory, it declines to adding new rows in a data storage. So we used the memory and disk mode to be consistent with other databases. And the last one was a age base. There were some settings for age region server. This is a process which runs on a data nodes. We configured a Java virtual machine heap size. And for Cassandra and HBase, it was set compression of data during write operations. It was a snappy compressor. The workloads. The workloads defines which type of operations we applied on a database during transactional phase. So we tested under 6 main workloads. On the diagrams, we'll see additional diagram for the workload which is not mentioned on this slide. So the workload A, it simulates a heavily updated system when amount of read and update operations is divided by 50-50. So it simulates, for example, e-commerce system when the data is updated and read. Workload B, it's so-called read mostly workload. It simulates, for example, content tagging system when most of operations are reading text and only some operations are updating. Workload C, it's kind of caching system when you just read the data from a cluster. Workload E, it's read latest. We have 5% of insert operations and 95% of read operations. It simulates working with user status updates or working with inbox messages. Workload F, it contains 2 types of operations. Complex operation as read data from database, modify one value, one field in a row, and then write data in database. And just a read operation in proportion of 50-50. And the last workload, which is described on this slide, is write heavily workload when 90% of operations are insert operation. It simulates heavy insert of data in a system or data migration. For every workload, we set the number of threads. It is a thread count as 100 threads. So operation count for each workload was defined as 10,000, and we worked over the data set for 100 million records. The results of tests, it is a number of operations which the system can support. It's called throughput, the number of operations per 1 second. And the latency of operation, how much time it takes to execute a single operation in a database for every client thread. So the first chart, it's for the load phase. When we loaded 100 million of records in a database, every record was in a size of 1 kilobyte. So in average, it was a data set of 100 gigabytes. It was slightly bigger for every system because for every system there are some additional data which are also stored with user data. For the load phase, we can see that the highest throughput is achieved for Cassandra and CoachBase. The lowest value is for HBase. For HBase, we configured we configured the system with auto-flash option. The auto-flash option confirms that when you put a value in a database, it is flushed from client side to the database. By default in HBase, you can use a client cache which collects some amount of the data for put operations and then flashes the cache from client side to the database. For CoachBase, we can explain the highest throughput because the CoachBase essentially is a memory distributed solution and which in asynchronous mode writes the data proceeds the data on disk. For Cassandra, the data is written in commit log and on a disk to provide persistency and recoverability. And additionally, the data are stored in a memory in a mem table. So the CoachBase and Cassandra, they are pretty fast when you insert the data. And we'll see the confirmation for fast insert operations on the next slide as well. For each workload, we'll see two charts. Workload A update operations. So HBase and Cassandra, they provided latency less than 20 milliseconds, but the performance, the value of throughput for Cassandra is limited to less than 2,000 operations per second. The latency for Mongo database it increases from 20 milliseconds to 100 milliseconds, and almost the same behavior we'll see on the next slide. So we also should keep in mind that the tests were executed in a cloud environment where we used network storage, because essentially Elastic Block's storage volumes, they're network storage. So it should be also kept in mind. And for example, if we run the same set of tests on hardware, the results can be slightly different, but trends are essentially the same. For the read operations, there is no leader. For CoachBase, we can see the latency peak as well. Okay, the next workload, update operation, 5% of. Also for Cassandra and HBase, we see pretty low values for the latency, but for Cassandra, throughput starts to decline at the amount of less than 1,500 operations. For the Mongo database, we intentionally left on the chart the points when the throughput decreases, and the latency increased. So the next slide is for the read operations. Here we can see that almost all databases have the same behavior, but the Couchbase has the latency which evenly increases with the value of throughput. Workload C, when we have only read operations, almost the same graph for Couchbase, and we have number of latency peaks for Cassandra and HBase. We suppose it can be explained due to the fact that tests were executed in cloud environment, and we used network storage. So the latency for Mongo databases increases. It's almost the same behavior for all workloads. But maximum values for throughput, number of operations, they're for Couchbase and Mongo database. So if we just need to have a maximum value of operations per second and latency, let's say it's less than 100 milliseconds, so the Couchbase and Mongo database are fine. For Mongo database, they heavily use a memory, so they have memory mapped files, and they are pretty good with workloads where we have read operations. Workload D, 5% of insert operations. As we saw in previous charts, Cassandra and Couchbase, they're very fast. Almost all latencies for all throughputs, they are less than 5 milliseconds. For Mongo database, the latency increases, but at the same time we have almost the same throughput value for as for Couchbase in Mongo. 95% of read operations in this workload. So the Mongo database is quite close in low value of latencies to Cassandra and Couchbase. As I already explained, they use memory mapped files, and if we deal with mostly with read operations, the Mongo provides good results. The workload E, which was not described on the slide before charts, it was not mentioned intentionally because it is about scan operations. So the scan operation in workload is defined you do a short scan of keys in sequential order, starting from a random value of the key. Scan operations, they are not supported in Couchbase. And for Mongo database, we don't have a graph because the values of latency for Mongo database on a scan operations, they were higher than 2000 milliseconds. So they are significantly greater than for Cassandra. And for HBase, we also limited, we noticed that the maximum throughput, maximum number of operations for scan is limited almost at the 50 operations per second. So at the same time, Cassandra is pretty good for scan operations. The value of throughput is less than 250 operations at that time. So it's kind of a special case for databases. In some databases we don't have at all scan operations, but systems which support scan operations, they do not deal pretty good with such type of operations. Workload F, where we have complex operations, complex operation, reading the data, modifying a value, and then writing back to the database. It's a read, modify, write. And the first chart is for read operations. So there is no leader, but the most predictable behavior for latency is for Couchbase. One important note for every chart in this presentation is the points for every graph. It's an actual value of throughput. At the same time, when UCSB applies a workload to the database, we identify the desired throughput, how many operations we want to achieve with the system. For example, we set for the workload, we define that we want to achieve 2000 of operations per second. And the actual result was, for example, 1700. So on every graph, we see the actual value for operations per second. Update part of read, modify, write. So as we saw in the previous charts, Couchbase, Cassandra, and HBase, they are very good in updating data, in inserting and updating the data, and the complex operation as a summary, which is read, modify, write. So it's a sum of two previous charts. So we can from this chart we can define that three databases are pretty good with the mixed workload. When we read data and we update the data in the same amount of 50%. The last workload is about heavily inserting data. Cassandra and Couchbase, they are very, very fast. less than 5 milliseconds, and almost the same value for throughput. HBase at the same time, we can see that the latency is evenly increases. And for the Mongo database, we have a maximum throughput of 4,000 operations, which is not so small for 4-node cluster. And the last graph, the last chart is for 10% of read operations. So we can see that all solutions they have some kind of unpredictable behavior for the read operations. Okay, so what is the conclusion about evaluation? So we have a very wide range of different systems. There are 4 types. To choose a variant of solution which can be applied to your system, we can identify which are typical application operations, and then we can define, not define, but identify the data set. So how much the data we're going to put in database, or just also we can define, not define, but potentially identify if there is a data model and how it can change during life cycle of the system. If there are some transactional replication and consistency requirements, probably in most cases we need a replication to have a failure-tolerant system. And as for consistency, it's also an important factor because, for example, in Cassandra, we can define different levels of consistency for every operations. We can define or identify the performance requirements in terms of how many operations should be supported by a system. And if it's kind of migration type of project, it's important to define if we can and how to migrate the data from existing system. Then we can test and evaluate the performance using the approach which I described. And the good way is also to build a proof of concept for a system, which can confirm or decline the architecture which we supposed to have in a system. And the last statement says that there is no better perfect solution. Every solution can be good in a specific case. And for example, building a proof of concept can identify which solution is a good and which solution is not good for our system. That's all that I wanted to share today. Thank you very much for attending the session.